Now, another feature that you might have noticed in this picture with the graphs of 1, 2, and 3 vertices is that many of these graphs look very similar. If you look at this one here and the one next to it, surely you agree that these are the same thing. The only difference is that now it is xz that are connected by an edge and y is by itself. But both graphs consist of two nodes connected by an edge and an extra node not connected by an edge. And similarly with this graph. And you notice corresponding similarities between the graphs of with two edges. So I'm marketing these as different graphs, but really this is false marketing. So how do we deal with this horrible false marketing? We introduce the notion of isomorphism. So we want to be able to tell what it means that the graphs look essentially the same. This concept is a concept you might have seen in different areas of mathematics depending on which courses you have taken. There are isomorphisms of vector spaces. If you've studied algebra, there are isomorphisms of groups and so on. So let's look at what it means for graphs. So two graphs are called isomorphic if there is a one-to-one correspondence between their vertices so that the number of edges between any two vertices are the same as between the corresponding vertices. Let's look at an example and then talk about what this actually means in plain English. So let me consider the same example I drew here. Say I have this graph with edges x, y, and z, and I have, let's use a different color. So I have this graph. Let's call the edges, the vertices A, B, and then C. So what is this one-to-one correspondence that I am talking about? Well, if we map the vertex X to the vertex A, the vertex Y to the vertex B, and the vertex Z to the vertex C, we get a one-to-one map or one-to-one correspondence between the vertices of the XYZ graph and the vertices of the ABC graph. But not only that, our correspondence is in such a way that the number of edges between X and Y, which is 1, is the same as the number of edges between A and B. And the number of edges between A and C, which is 0, is the same as between X and Z. So our isomorphism is the map that maps X to A, Y to B, and Z to C. And another way of putting this number of edges business is that the map respects the structure of the graph. It's not just mapping vertices to vertices, but we do it in such a way that the edges come along exactly as we expect them to. So, in other words, the isomorphism is a bijection between vertices that respects the structure of the thing at hand, in this case, the graph. If you have seen this notion before in terms of groups or rings or vector spaces, you might remember that in those cases, an isomorphism is a bijection that respects the algebraic structure. So the multiplication of the group, the multiplication and addition of the ring, and so on. If you don't know what these things mean, don't worry, you don't need them for graph theory. I'm just trying to illustrate how this is a widely used concept in mathematics. So it seems that this business of essentially the same graph is a business of relabeling. I mean, what did we do here with the graph from before? We took the vertices X, Y, and Z, and in the green example, they are labeled A, B, C instead of X, Y, Z. So just changing the names. And because this is possible, the labels are not very important. Both the two examples are really trying to convey this general idea: a graph with 3 vertices, 2 of whom are connected with an edge. And this is an unlabeled graph. So often graphs will be unlabeled, and if you want really to make sure that this unlabeled graph and this unlabeled graph are isomorphic, you can label them. And then you just connect or make the vertices correspond in such a way that you get an isomorphism of the labeled graphs. So let's look at a few other examples. So let's look at this example and this example. So the question is, are these isomorphic? And the answer might be deceiving. So you might think that yes, they are, because you have 3 vertices in both and you have 3 edges in both. But the edges go in the wrong place. So if I label these graphs, so I have A, B, C and X, Y, Z, the problem I will run into is that if I map B and C to whichever vertices here, however I do it, I will only get vertices with 1 edge between them. This graph doesn't have any vertices with 2 edges between them, while this one has. So I will fail in my effort to map the vertices to vertices in such a way that the number of edges is preserved. That is the reason why these are not isomorphic. And the shorthand for this is this sign, not isomorphic. So here you get this idea that isomorphism is really about preserving the structure of the graph. Let's look at another example. You have the pentagram, this star that you always see kids drawing at school. Let's call the vertices A, B, C, D, E. And then you have the usual pentagon. And let's call the vertices U, V, X, Y, Z. Now my question to you, are these graphs isomorphic or not? Can you find a one-to-one correspondence between the vertices that respects the edge structure? Please pause the video and think about this. Okay, welcome back. I claim that they are isomorphic. So this means isomorphic, despite the fact that pictorially they look different. So let's find an isomorphism, and I'll do it in the following way. So I will start with this one. So if I map U to A, U has an edge with V, A has an edge with C. So maybe if I map V to C, V has an edge with X, C has an edge with E. So I will need to map X to E. There might be other possibilities, which is just one isomorphism. Now, next is Y. From E I can go to B. And from Z I can go to D. And Z has an edge with U, and D has an edge with A. So I'm back, and you can check that, for example, between V and X, there is exactly one edge, as is the case between C and E, and so on. So how you draw the graph is an aesthetic thing. The only thing we care about when it comes to isomorphism is which vertices are connected, and in case of multigraphs, or in case of not simple graphs, by how many edges are they connected. As an exercise, I would like to ask you to draw all the connected simple graphs with 4 vertices. So I did this in part for 1, 2, and 3 vertices. Now I want you to revise the definition of connected and simple and draw all the 4 vertex cases. Then I want you to count how many there are with labels. So you can label the vertices X, Y, Z, and W. So how many possible graphs are there, and which ones are isomorphic and which are not? That is your exercise.